Hello, my name is Kevin Connell, and thank you for joining me on my presentation on adiabatic logic, a means for reducing power consumption in CMOS circuits. We're going to start off today by talking about what adiabatic actually means, and then going over the rules of adiabatic and why it's better than traditional CMOS circuits. We're then going to go into some details on different adiabatic approaches, and then we're going to conclude by talking about the pros and cons of adiabatic over traditional CMOS designs. So what is adiabatic logic? Well, according to the New Oxford American Dictionary, the term adiabatic is defined as relating to or denoting a process or condition in which heat does not enter or leave the system concerned. In other words, an adiabatic system is one that does not waste energy. This term has its origin in thermodynamics, where a system's heat energy remains constant over time. For circuits, this energy comes from inefficiencies in the electronics. When developing logic circuits, adiabatic logic is a process used to reduce the power consumption and reduce heat by extension. This process is done through something referred to as reversible logic. Since most designs are CMOS these days, much of the research into adiabatic logic focuses on modifying traditional CMOS designs to make them adiabatic. So now you might be asking yourself, why is reducing power consumption important in the first place? Well, there are a few key advantages. First, it's important to note that current circuit designs are limited by their heat output. In many cases, transistors are capable of switching faster, but because of the heat they generate, we cannot design faster circuits to take advantage of this. Secondly, there are many devices where power consumption is extremely important. This includes mobile devices such as smartphones and smartwatches, as well as Internet of Things devices such as smart door locks, which need to run months or even years off of a very small energy source. Third, there is an opportunity to reduce energy consumption and by extension reduce the environmental impact through adiabatic logic. And while adiabatic logic is more complex, the improvements in manufacturing transistors on smaller process nodes makes this technique more feasible. It's also important to note that as circuits get smaller and faster, they tend to increase their energy consumption per unit area. Adiabatic logic may help alleviate that. So next up, we're going to talk about the rules of adiabatic logic. With adiabatic logic, there are two generally agreed upon rules that need to be followed. These rules, if followed, will significantly reduce the total power consumption of the system. The first rule is that a transistor should never be turned on when there exists a voltage potential between the transistor source and drain. And the second rule is that a transistor should never be turned off when there is current flowing through it. If you think about it, these rules are basically opposites of one another. In both cases, you don't want a transistor to switch states when it has control over the flow of electricity through the gate and drain. To explain why these rules are important and how they reduce power consumption, we must first look at where traditional CMOS designs waste energy. Despite the efficiencies of CMOS circuits compared to other technologies, they still consume and dissipate a measurable amount of energy as heat, particularly during switching. One of the primary components of this energy comes from the need to charge and discharge the gate capacitance C through a circuit that has a resistivity R. The equation below models the energy loss with a given switching voltage V, capacitance C, resistance R, and switching time T. As you might be able to tell, if the switching time can be increased, the energy consumption of the circuit can be decreased. I should note, however, that this assumes that there is no short formed between VDD and ground due to the pull-up and pull-down networks being active simultaneously. For traditional CMOS designs, T is generally proportional to R times C. If you look at the graph on the right, which shows power draw over time for this model, area under the curve can be considered proportional to CV squared and is the energy dissipation of the circuit. You might have heard me mention the term reversible logic earlier. Reversible logic here is based around the idea that the switching time T can be increased to reduce energy consumption. This can be done because transistors typically take significantly less time to switch than the cycle time of the system's clock signal. By taking longer to switch, this spreads out the charge time over the entire clock cycle, which reduces energy dissipation across the gate. As a side effect, this also reduces the power demand on interconnects and power rails. To spread out this charge time, we must not turn on a transistor with a large potential between the source and the drain. As you might remember, this is the first rule of adiabatic logic. The second rule of adiabatic logic says to avoid turning off a transistor when current is flowing through it. This comes from the fact that transistors do not shut off instantly. And this is exacerbated by the fact that transistors change states even more slowly when gate voltage takes a while to change. Gate voltage is likely to change slowly too, as it's frequently controlled by another transistor with a long transition time. During shutoff process, there is a voltage drop across the transistor, but not enough resistance to completely stop current. This results in more energy consumption and dissipation. As far as increasing the switching time T is concerned, we want to increase voltage over a longer period of time. And this can be accomplished using triangular or trapezoidal clock signals instead of the traditional square wave clock signal. Below is an example output from an NMOS inverter using this approach. Now that we have a basic understanding of the foundation of adiabatic logic, we can start talking about the various adiabatic logic approaches. The first one is SCRL. So for the first logic approach here, SCRL, or split-level charge recovery logic, this technique was developed by Knight and Nernst, and it utilizes a pair of trapezoidal clock signals that rest at 0 and VDD for 1/4 clock cycle each. This technique requires transmission gates that slowly change the output signal between 0 and VDD. Besides the transmission gates, transistor gates, which are initialized at VDD and ground, the rest of the circuit starts at VDD over 2. Transmission gates, transistor gates, slowly swap voltages with each other to facilitate a slow ramp in gate output. To explain how split-level charge recovery logic works, we have a diagram on the right here which shows an AND gate that facilitates this principle. Phi1 and /Phi1 are trapezoidal clock signals used instead of VDD and ground. P1 starts off at ground and /P1 starts off at VDD, which turns off the transmission gate. At the beginning of the process, the clocks Phi1 and /Phi1 are at VDD over 2. Clock Phi1 cycles between VDD over 2 and VDD, while clock /Phi1 cycles between VDD over 2 and ground. To further explain how this whole process works, we're going to break it down to steps here. So, in step 1, the values of P1 and /P1 slowly switch. This turns the transmission gate on. Step 2, Phi1 slowly rises to VDD, while /Phi1 slowly falls to ground. In step 3, the left half of the circuit computes the NAND result like normal. And then in step 4, once output is used, the transmission gate closes. This slowly reverts P1 and /P1. For step 5, Phi1 and /Phi1 slowly return to VDD over 2. One thing that's important to note is that you cannot change A and B until Phi1 and /Phi1 reach VDD over 2 to avoid violating Rule 1 of adiabatic logic. Now if you've looked closely at this diagram on the right, you'll see that there's an extra PMOS gate connected to B down in the bottom half. We have it circled in red here. This here we can explain by going through a scenario. So imagine the situation where A is equal to 1 and B is equal to 0. Once Phi1 and /Phi1 reach VDD and ground, current flows from Phi1 through the B PMOS, and then since A is 1, there is a high voltage applied to the A NMOS. This voltage across the NMOS causes heat dissipation. By having the PMOS in parallel with this NMOS, we can prevent that extra heat dissipation from occurring. That concludes your brief overview of the SCRL split-level charge recovery logic version of adiabatic logic. The next approach to talk about here is 2LAL, or two-level adiabatic logic. So 2LAL, or two-level adiabatic logic, the second approach we're looking at here, was developed by Michael Frank in Physical Limits of Computing. Compared to existing techniques at the time, this one was unique because it required only basic switching devices. The figures at the right show the basic building blocks of 2LAL. It consists of a pair of transmission gates which transmit A and A bar. These are represented together as a single box on the left there. A benefit of 2LAL is that inverters simply require you to cross the B and the B bar lines. This makes inverting easily possible without extra gates. It can also do both latching and logic with the same structure. To help explain this two-level adiabatic logic approach, we have an example that you can see on the right here. This is an example of a buffer created from transmission gates, where phi1 and phi0 are trapezoidal clock signals, but phi0 is 90 degrees ahead of phi1 in phase. Thanks to this extra phase offset, the circuit can function properly. To help explain how this circuit works a little bit better, we're going to go through it step by step. So for step 1, there are two parts. In part A, all the nodes start out at 0. IN, the input, begins to slowly change to 1 if the input is supposed to be 1. And in part B, at the same time, phi0 slowly changes to 1. For step 2 of the process, phi1 slowly changes to 1 as well, which slowly brings the output to the previous input state. Step 3 then has phi0 transition back down to 0 and pulls in down to 0 along with it. And then step 4 transitions phi1 to 0, and then the output is brought down to 0 by the next gate in the pipeline. By performing the process in these steps, we can ensure that both rules of adiabatic logic are abided by the entire time. So that should conclude our brief summary on a couple of different fully adiabatic approaches to the problem. The next part of this, we're going to talk about the differences between fully adiabatic, which is what we were discussing, and another approach, which is quasi-adiabatic. So, to discuss this, first we must recognize what fully adiabatic systems are. Fully adiabatic systems only experience energy loss due to the non-ideal switching from leaking currents. This means that you don't lose energy by directly connecting VDD and ground or by having any of the rules of adiabatic logic violated. Quasi-adiabatic systems, on the other hand, lose energy to non-adiabatic components of operation. As we mentioned earlier, all the previously mentioned techniques were fully adiabatic. By contrast, some quasi-adiabatic techniques include efficient charge recovery logic, or ECRL, positive feedback adiabatic logic, or PFAL, and true single-phase adiabatic logic, or TSAL. The figure to the right here compares a couple of different adiabatic approaches and quasi-adiabatic approaches to sort of illustrate in a general sense how they compare to each other in terms of energy loss. When looking at that figure, you might be able to realize that SCRL, our fully adiabatic approach, does significantly better than the quasi-adiabatic approaches also listed in that figure. So, with quasi and partially adiabatic techniques, there are a few primary ones, a couple of which we listed on the previous slide. These include the efficient charge recovery logic, ECRL, the positive feedback adiabatic logic, PFAL, the true single-phase adiabatic logic, or TSAL, and the NMOS energy recovery logic, NERL. All of these techniques are partially adiabatic or quasi-adiabatic in some sense, meaning that they don't abide by the two rules of adiabatic logic in all situations, but instead try to mitigate the effects of energy loss in traditional CMOS designs. Here we have listed alternatively a few of the most popular fully adiabatic techniques that I've seen. A couple of these techniques we discussed before. This includes split-level charge recovery logic, or SCRL, and two-level adiabatic logic, or 2LAL. Additionally, what we haven't discussed before are other techniques such as two-phased clocked adiabatic static CMOS logic, or 2PAS-CL, and pass transistor adiabatic logic, PTAL. While there isn't enough time to fully go into how each of the quasi-adiabatic and fully adiabatic techniques work, I wanted to give you a brief overview of what exists out there, and you can understand that all of these approaches work in fairly similar ways and try and reduce the extra power consumption used by abiding by the two laws of adiabatic logic. Now that we've discussed a few of the different techniques for fully adiabatic and quasi-adiabatic logic, or partially adiabatic, you might be wondering what the difference is between these two techniques and why you might want to use one over the other. One important note to make is that partially or quasi-adiabatic solutions tend to require fewer transistors. This is because these adiabatic solutions tend to be a lot simpler when not fully implementing the two rules of adiabatic logic. Additionally, because of this extra simplicity, they tend to be cheaper to design and produce, and a lot easier to implement into existing logic systems. Fully adiabatic solutions, however, tend to have no waste energy, or at least no waste energy in ideal situations. There is still some energy lost due to inefficiencies in the transistors because they aren't perfect switches. So we're getting near the end here, but before we conclude, we need to talk about the pros and the cons of adiabatic logic, specifically why you might want to use adiabatic logic in certain situations, and why adiabatic logic may not be the best for other situations. As with almost anything, when it comes to adiabatic logic, there are a number of disadvantages and advantages. We can start off here by going over the disadvantages. One of the main disadvantages is that adiabatic logic approaches tend to require more transistors, which takes up more space and adds a lot more complexity to traditional CMOS designs. Adiabatic logic also requires, in many situations, precise control over clock voltages to create the clean trapezoidal waves or triangular wave signals required by the logic designs. On top of that, adiabatic logic sometimes requires slower clock speeds, so that way transistors have the chance to switch on more slowly. Of course, alongside all of those disadvantages of adiabatic logic, there are a number of very notable advantages. Primarily, this is all based around the fact that adiabatic logic tends to have lower power consumption. This can result in batteries for devices that need them to last significantly longer, as well as significantly less heat generation and a much lower environmental impact, making adiabatic logic possibly one of the better solutions for combating climate change, as our world increasingly depends on electronic devices, which consume significant amounts of power. So now that you understand some of the reasons why you may or you may not want to use adiabatic logic, we can briefly summarize what we've talked about, and then I'll be open for questions. To summarize what's been talked about during this presentation, I'd like to go over a few key points and takeaways. First, it's good to remember that adiabatic logic is designed to prevent any waste energy that you might see created in traditional CMOS designs from inefficiencies in switching. With existing CMOS designs, you see a lot of energy loss due to switching because of various effects regarding transistors that either have voltage flowing through them or current flowing through them. These sources of loss allude to the two rules of adiabatic logic, which we can follow to ensure that we can minimize the amount of loss seen in circuits. The first of these two rules is that you should never turn on a transistor when there is a voltage potential between the source and the drain of that transistor. And the second of these rules is to never turn off a transistor when current is flowing through it. By abiding by these rules, we can minimize the amount of energy loss in the system. Additionally, it's important to note that we can decrease the amount of energy consumed and by extension the amount of energy dissipated in a circuit by slowly changing transistors between states. This transition can be achieved in a slow fashion through the use of trapezoidal clock signals or triangular clock signals, which can allow the input of each transistor to be slowly changed, and by extension the output of that transistor to be slowly changed between high and low voltages. The last point to take away from this presentation is that while adiabatic logic has a significant reduction in energy consumption in some situations, it also tends to be a more expensive solution to implement and more complex, as well as requiring, in some situations, slower clock speeds, which may reduce performance. However, in situations where performance is less important than energy consumption, you may find that adiabatic logic is the better solution to your problem. This concludes my overview on adiabatic logic systems. and why you may or may not want to use them. Here are references which I used throughout the paper. If you have any questions, please let me know, and I'd be happy to answer them. Thanks for joining me, and have a great day.